Line integrals along a curve of a force can represent work. Here's our definition. If C is a smooth curve, which is parametrized by R, T between some bound A and B, F is a continuous force field over that region containing C, then we can calculate the work done in moving an object from point A, capital A here at T sub A, to point capital B at T sub B. So we traveled along the curve and we are able to calculate the work done by this force to move something along this curved path. And you'll see the definition is the same definition we've previously been using. It's the line integral of the force field dotted with the tangent unit vector with respect to the arc length, or rather the composition of the force field with the parametrized curve inside of it, and then the derivative or that velocity vector with respect to t. And this should make sense. You may recall, you should have learned somewhere previously in a math class, or maybe physics, that work could be defined as that force vector dotted with d, the distance vector. And your book shows different ways to write the work integral for f defined as mi plus nj plus pk over the parametrized curve c. And so we have our definition, our vector differential formula, the formula that we've been using in the past couple examples, our parametric vector evaluation, but there are some other different ways you could think about writing this that still mean the same thing. So we're still taking each of those m, n, and p components and dotting them with the derivative in these other two notations. And this is just to show you, hey, we have all these different notations, but they still mean the same thing. So the line integral of a force field along some path can represent the work done by that force. Let's look at an example. In this example, we're going to find the work done by the force field along the curve parametrized by the path r of t equals sine ti plus cosine tj plus t divided by 6k. From t increasing from t equals 0 to 2 pi. And this idea of increasing is really important as we start to move forward and we build towards Green's theorem, because we're always going to be evaluating these integrals over a direction. So our force here is defined as 6zi plus y squared j plus 12xk. So in order to calculate the work done by this force along the line integral, well, we need F composed of R of t. So 6z, I'm going to plug in t over 6. That's just going to give me ti. Y squared, my y value is cosine t, so I'll have cosine squared tj. And then 12xk, sine t is going to go in for that x. And I have plus 12 sine t k. I also need my derivative. So the derivative of r with respect to t, the derivative of this sine component, I have cosine t I plus the derivative of cosine t, which is actually going to be minus sine t j, plus the derivative of t over 6, which is just going to be 1/6 k. Once I have all of these pieces, then I need to find the force field dotted with dr dt, which is going to give me t cosine t minus sine t cosine squared t plus 2 sine of t. And that was just the dot product of each of these x, y, and z components. Once we have that, then we know that the work from A to B of that force dotted with dr dt, which gives me the integral from 0 to 2 pi, because that was what my t was specified over, of each of these 3 terms. So I'm going to write that out. I've got the 0 to 2 pi integral for t cosine t dt minus the integral from 0 to 2 pi of sine t cosine squared t dt plus 2 of the integral from 0 to 2 pi of that third term, sine t dt. And you don't have to separate it like that. You can write this as one big integral with just one integral sign in front. But this first piece would be integrated using integration by parts. The second piece will be integrated using AU substitution. I think it is long and drawn out for me to go over all of those steps with you right now. So I'm just going to pause and write out my work and give you the answer. And the answer for this whole problem, I'll go ahead and tell you, is 0. If you want to pause and try to get there, see if you can. So I wrote out some of my steps here for my integration by parts. I still have one integral in there, my u sub, that's going to become 1/3 u cubed, or 1/3 cosine cubed t. And then sine t is easy for us to integrate. It just becomes negative cosine t. And this is what it looks like once you've integrated it, evaluating it at 2 pi and 0. Of course, at 2 pi and 0, t sine t, that's going to go to 0. So you're really just looking at the cosine terms at 2 pi, and 2 pi and 0 are the same. So you're going to get the same plugging each of those in, which gives us a final value for this integral of 0. There's 0 work done by the force to move whatever we're moving in the direction of this increasing t from 0 to 2 pi along my curve.